All right, party people, let's get into topic 4.5, everyone's favorite S word, stoichiometry. So one thing we're looking at is the fact that no mass is lost or gained. This is a very key property of the world, or it's a law. But mainly what we're looking at is this learning objective. How do the reactants and products change based on the balanced equation for any chemical reaction? So generally, when we talk about stoichiometry, we're talking about mole conversions, but we also need to know how to balance a chemical equation. We also need to know the conversions that go along with moles. So other conversions are like grams to moles. We might need to do that first. We might need to do things like, oh my God, just freaking, yeah. Might need to go like liters to moles. We might need to go from the other way, like moles to grams. We might need to go moles to liters. So lots of different conversions we can do just depending on what we're asked for and what we're given. So ultimately, we have to read the problem. Remember, RTFQ, read the full question so you know what you're actually talking about. Now, those of you who had me for intro chem know this island sheet. This is a slightly older version, so I added something last year. So current 11th graders will recognize this. Or we'll recognize another island here, but we'll talk about that. Generally, this just tells us that if you are given something about a substance, that is your known substance. That is substance A. That's what you're starting with. And if you are trying to convert to an unknown substance, the only bridge that gets you there is using mole-to-mole conversions, which come from your balanced equation coefficients. So if I'm given grams, right, if I start with, hey, I've got 10 grams of magnesium, and I'm asked, how many grams of oxygen will I use up? I can't just go straight grams to grams. Can't do that. I first have to go to moles of magnesium using my molar mass. I can then use the coefficients from the balanced equation to get moles of that new substance, oxygen, and then I can use the molar mass of oxygen to finally get to the thing I was asked for. Yay! Okay, now what are we actually doing with this? Well, one of the things we often talk about are the limiting reactants. So it's not always just as simple a question as, you know, here's one reactant, how much of the other reactant will I use up? Sometimes we get two different values for two different reactants, and one of them limits how much we can make. So the limiting thing just runs out first. The thing that's left over that isn't completely consumed is our excess reactant. You can think of this in the classic example of making grilled cheese. Let's say I have 6 slices of bread, and then I have 1,000 slices of cheese. It's pretty typical fridge stash for me. How many sandwiches can I make? Well, it's pretty clear which of these is going to run out first, right? The bread is going to run out first, unless I'm making some really gross, mega cheesy sandwiches. I'm going to use up my 6 slices of bread first, and if there's 2 slices of bread per one sandwich, then I'm going to make 3 sandwiches. And then I'll have used, let's say I use 2 slices of cheese per sandwich. I've taken away 6 slices of cheese, so I would have minus 6 994 slices left. Okay, that is basically what we are doing with limiting and excess reactants, but obviously it's a little trickier with mole conversions. So here's an example. We've got iron and oxygen reacting to produce rust, which is given with the formula Fe2O3. So we're told we have 15 grams of iron, 6.5 liters of oxygen gas at STP, and we're asked how many grams of rust that iron oxide would form. So before we start this, we're going to need our balanced equation. So we're given iron. We're told we're pairing it with oxygen gas. Oxygen is diatomic, so it'll be O2, and it makes only one kind of compound. So this is a synthesis reaction. So when we look at balancing this, we're going to want 2 irons to balance out with the 2 on the right, and we have 3 oxygens on the right but 2 on the left. So we're going to need to get a common multiple of 2 and 3, which is going to be 6. So to get 6 oxygens on the left, I'll put a 3 there. To get 6 on the right, I'll put a 2 here. But then this has made my iron up to 4, so I'll need a coefficient of 4 here. So 4 irons, 3 oxygens, 2 rusts. Okay, now that the equation is balanced, let's map out how we actually want to go about this. So to figure out how many grams of iron or liters of oxygen is going to get used up, ultimately what I'm trying to do is figure out grams of rust, right? So mass of the iron oxide. So I'm going to set up 2 different pathways. One is going to be with the iron. So I'm going to say, okay, 15 grams of iron, and I want to see how many grams of rust that makes. So to do that, first I need to get 2 moles of iron using the molar mass of iron. And then from there, I'll go to the moles of rust, iron oxide. And then using the molar mass of iron oxide, I can find the grams of iron oxide. Okay, so that'll be our one pathway. The other option is, what if we say how much will the oxygen make? So 6.5 liters of O2. And we're trying to end up, again, in grams of rust. 2O3. Same thing, we're going to need to find moles of oxygen using not the molar mass, but the liters to moles conversion from this guy, is that if you are at STP, there are 22.4 liters of gas in a mole. And again, that's only for gases. So we have to be careful about the conditions we're given. But once we're in moles of O2, we find moles of the iron oxide, and bada bing, bada boom. Okay, so to plug things in here, 15 grams of iron. Zoom in just a hair. The molar mass of iron is 55.85. So that's going to go at the bottom. That's how many grams of iron are in 1 mole. So I always want to put the unit I'm trying to cancel out with opposite the unit that I'm trying to cancel out, right? So grams on the top, grams on the bottom. And you'll notice I always label things. So it's moles of iron, grams of iron. The reason that's important is we are converting to a new unit of a new substance. So we want to make sure we're tracking things. So there's 4 moles of iron for every 2 moles of the iron oxide. So I'll put a 4 moles Fe for every 2 moles Fe2O3. And then lastly, we're going to find the molar mass of iron oxide to convert it into grams. So 1 mole Fe2O3, and I'll have to punch this in real quick. 2 times 55.85 plus 3 times 16 gives us 159.7 grams in 1 mole of iron oxide. So to punch that in, 15 over 55.85 times 2 over 4 times that gives us about 21. Yeah, let's just round it to 2 sig figs because that's what we were given with our mass of iron. So that's how much that would make, but I don't know which one is actually limiting, so I'll have to do it with the oxygen. So 6.5 liters of O2. To convert that to moles, I'm going to use that 22.4 liters per 1 mole conversion, which I can only use if I'm dealing with gases at STP. Then to get moles to moles, this step, I'm looking from the O2 to the Fe2O3. So this is a 3:2 ratio. 3 moles of O2 on the bottom for every 2 moles of iron oxide on the top. And then my last step using the molar mass, I already calculated it when I was doing this from the iron's perspective. So I can just retool that 159.7 number. 159.7. And then same thing, I'm just going to plug and chug, and I'll see what I get. 6.5 over 22.4 times 2 over 3 times 159.7. And I get 30.89, so I'll just round that up to 31. Okay, so one of these reactants, if I use it to completion, will give me 31 grams of iron oxide. One of them will only give me 21 grams. So which of these is the limiting reactant? Well, it's the one that gives me less product, right? Like the bread and the cheese example, the cheese would have given me more sandwiches, but the bread ran out first. So the 6 sandwiches is how much I could actually make, right? The lower value is how much we can actually make. So 21 grams of rust is how much I can actually form, and that was the question. How many grams of rust would form? We could also ask, just what is the limiting reactant? So iron is the limiting reactant here. Okay. So yeah, that's what's happening there. Now there's another thing we can do related to percent yield. So we theoretically can only make 21 grams of iron oxide. This is our theoretical yield because it's what math tells us we can actually make if everything was perfect and we made no lab errors. But if we only actually measured 19.8 grams of the rust, what does that mean? We do something called the percent yield. So we take our actual yield, which was that 19.8 value, divided by our theoretical yield, which was 21, and multiply it by 100. And again, the idea is to just give us an understanding of like how well we did to this theoretical ideal. So for that example, if our actual yield was 19.8 and our theoretical was 21, that's a pretty good yield. 19.8 over 21 times 100 gives us about a 94.3% yield of rust. So not bad. Yeehaw. Okay, I think this is the last example. Yeah. All right, so we've got 2 reactants here. We've got magnesium, that's going to be a solid combining with HCl, and we're asked about the percent yield because we made some hydrogen gas. So step 1 is writing the balanced equation. Now, I will note this is not something I am assessing y'all for this year. This is something we did in intro chem, is like writing equations and predicting products. It's not really something I'm going to be spending a bunch of time on, but this is a single replacement reaction. We know that because HCl, the H is kicked out to make hydrogen gas. So I know I replaced the H with a magnesium. So magnesium is now paired with the chloride. And then I would just go back and balance this. So I'll need a 2 there, and everything's good. Okay. So our second step here is identify the limiting reactant, okay? Given that we have 2 amounts of reactants, we need to know which one actually is giving us our theoretical yield. Now, this one is extra tricky because we're given milliliters of a molar solution, right? So we don't really have that island on the sheet or on the diagram I put earlier in the video. But ultimately, what a volume and a molarity of a solution can give us is moles. So we'll do that in just a sec. So similarly, before we get to percent yield, we need that theoretical yield. Again, that's step 2 and 3. Identify that limiting reactant. So I'm going to take the grams of magnesium first because that's easier. 24.31 grams of magnesium. And I'm trying to get into liters of H2 gas. So let me just write that up here. Grams of Mg to moles of Mg to moles of H2 to liters of H2. Okay, so my molar mass of magnesium is that amount, 24.30. That's a funny choice. So I've got 1 mole of magnesium, can already tell. Now the mole to mole values, it's going to be 1 to 1. If you look back at that balanced equation, 1 mole of magnesium is used up for every 1 mole of H2 produced. And then finally, to get to liters, we're not told this is at STP, but we should just assume that because I don't know, I forgot to write it. So ultimately, that cancels out with that. The rest are 1s. So we should make 22.4 liters of H2 if we're doing it this way. Now, if we are starting with the HCl, then we need to look at these 2 values. And this one's going to be a little different because ultimately we're just going to jump into the moles of HCl. We're not going to use a molar mass conversion or anything. We're going to use the molarity equation. We're going to rearrange this in order to get to the moles of HCl. So we'll have to do a little algebra. And then from there, we can just use our mole conversions using those balanced equation coefficients. And then we're in moles of H2. We'll use that 22.4 value to get the liters of H2. Okay, so what do I mean by rearranging the molarity equation? Well, as written, it solves for molarity, but we can rearrange it to solve for moles. So let's find the moles of HCl by doing the molarity times the volume. We'll have to convert our volume into liters. So 1 molar times 0.5 liters, not 500 mils, gives us half a mole of HCl. Okay, now I'm going to take this into my, conversions. So I've got moles of HCl. Now I'm getting the moles of H2 using my balanced equation. So it is a 2-to-1 ratio, 2 moles of HCl for every 1 mole of hydrogen gas. And then lastly, that 22.4 value to get moles back to liters. Yeehaw. Okay, and this one half divided by 4, so 22.4 over 4 gives us 5.6 liters of H2. Okay, so this one is our limiting reactant. That's our limiting reactant. That is our theoretical yield. So this was limiting reactant. And this 5.6 is our theoretical yield. That's if the thing that runs out first was fully used up. That is how much H2 it would actually make. Now for our final task of the percent yield, we need the actual over the theoretical. Actual over theoretical times 100. So our actual is given to us as 4.5 liters. So 4.5 is the numerator, the denominator is 5.6, so we made a little less than we expected. Multiply that by 100, and we get 80%. And I'm putting a decimal just to show that both of those are significant figures. Cool beans. Stoichiometry. It's cool. It's the S word. Yeehaw.